Topological optimization is the ability to take a currently designed part, or a part that is in the process of being designed, determine just what material is necessary to meet some sort of specific goal, and make the part ultimately lighter and as strong as it needs to be, or in some cases even stronger. Altair Inspire combines the easy-to-use interface of Inspire with the power and industry-leading topological capabilities of OptiStruct to make the fastest path possible from your current, potentially over-designed part to a lightweight, strong, capable part that will make your vehicle faster, stronger, and get you that much further in the race. With Inspire, we can take our currently designed part, or even a part that's in the process of being designed, and prepare it for an optimization. At the heart of the optimization is the design space. And the design space, think of it as a block of material that's going to be carved away. At its heart, that's what topological optimization is. It's like sculpting. A sculptor looks at a block of material and sees inside of it the part or the statue that they're looking to reveal to the world, and their job is to carve away the excess material. Topological optimization works the same way. You define the maximum amount of material that you can have, effectively determining what your design volume is, and you fill that with material. In the case of this currently designed part, we can utilize some of the aspects of geometry editing that we saw in one of the previous videos, particularly coming here to the simplify, and I'm going to come to holes, and I'm just going to double click on these holes here, and that's going to fill those up. And you see what we're doing is we're removing some of the lightweighting features that were already put in there kind of arbitrarily, and we're going to allow the optimization code to determine the ultimate shape of the part. Then I'm going to come here and I'm going to push-pull these. Oops. Let's undo that. Edit, undo. Sometimes those snaps can get you. Let me get out of here, and we'll just undo. There we go. A lot of times when I'm doing push-pull, I'll turn the snaps off just to make it a little easier. Okay, there we go. And we'll push-pull that. And we'll push-pull that. And push-pull that. And now that's a good block of material. You really want to have kind of a rough cut. The advantage being you tell it what space or volume your part can occupy, and the optimization code will determine what of that chunk of material is necessary. Now there are some aspects of this that have to be there. What we need to do is protect things like this mounting sleeve here, and also, as mentioned in the geometry, we can do that through partition. I can partition that, and maybe we'll make it 5 millimeters thick. And now what happens is this is going to be its own separate piece from this right here. And ultimately what we're going to do is we're going to select this as design space. But there are some more features on this we need to protect, and we're going to do that again through partition, and we need to protect these bolt holes here. Now if I select this as is, it's going to protect this entire little cube here, and I don't need to do that. I don't need that cube to stay there. The only reason that that little cutout is there is to allow me access to the top of the bolts that are going to mount this in place. So the fact that no material exists there already, that's enough of a definition. I don't need to protect that cube. So I'm just going to undo that and then come back to partition. And if you ever end up in a situation like this where it's protecting more than, or partitioning more than you need it to, just simply hold the control key down and left click on the faces that connect what you want to protect, which are this cylinder here, to the rest of it that you don't need to protect. And by control clicking on that, it removes those faces, or that connecting face. And now if I select these, since there's nothing connecting it to the rest, it will just fix the cylinder, which is exactly what I want. So let me bring it around here, and we'll deselect these, and I'll grab these. And 3 millimeters is fine for these. If I go much larger, it's going to begin to get close to the edge. And then finally deselect and grab that. And now that is exactly what I need to be for the design space. So you could go a couple of different routes with the design space. You could create the design space in your CAD system. And remember that the idea here is to have a nice big blocky chunk of material. We're not going to put fillets on here. We're not going to clean it up. We're not going to make it pretty. We're not going to refine it. We want this nice big block of material. The refining comes after we do the optimization. There's a possibility we can have some higher stress in these corners here because we don't like sharp corners, but we're not worried about that right now. What we're worried about right now is getting that design space defined. And we want it to be as nice and big and blocky. And if you want to know the details behind that, the smaller the features you have on your model, the smaller the mesh has to be, and the longer the analysis of the optimization is going to run. So we don't want to mess with small features right now. We just want large, big blocks of material. And from that, the optimization code is going to determine what is necessary. So now that we have the design space and non-design spaces set up, we need to make sure we have appropriate loads in there. And if you go back and take a look at the setting up analysis, structural analysis video, you'll see how to set those up. So we won't go through and set those up. We'll just have them appear here. And now everything is set to begin to set up the optimization parameters. Now remember, if you have multiple load cases, as we do in the case of this, we've got a vertical load and a lateral load. Multiple load cases for a structural analysis will give you two results. Multiple load cases in an optimization will guarantee that your part is prepared or is optimized for both of those load cases, or as many load cases as you put in there. So it pretty much guarantees that that your part is going to meet the requirements for all of the different load cases. So anything that you feel that the part might encounter, definitely include that load case. Definitely don't overdo it. The more load cases you put in, the more you limit your ultimate design. But if the load case is important, you absolutely want to incorporate that. So for analysis setup, for optimization, really the only other thing that we have for a parameter to set up here is for the shape controls. And shape controls deal with manufacturing constraints and shape constraints. So shape constraints are our symmetries. And we have three different options. We have symmetric, cyclic, and cyclic symmetric. Symmetric is just going to be pure planar symmetry. Cyclic and cyclic symmetric deal with things that are symmetrical about an axis, or rotational symmetry. Cyclic just guarantees that you have the exact same shape at each one of the different partitions that you set. Cyclic symmetric not only guarantees that you have the same feature in each one of the partitions you set, but that individual partition acts as a plane of symmetry as well. So the design will be symmetric about that, and then also copied around. So you can kind of see the difference between the two icons here. I'm just going to use pure symmetry. When I select my design space, it will put up the different symmetrical planes there, and they are all turned on by default. So I need to turn off or left click the ones I don't want, and I just want to make sure that the part is going to be symmetric about that plane right there. So now right click to leave there, and we get this little pink plane. The advantage to this is, since I have a load going in this side, in this direction, it will guarantee that anything I do going in that direction is copied going in the other direction as well, which will allow me to use this part universally, essentially make the part work on both the left and the right sides of the plane. So now we can talk about manufacturing constraints. Manufacturing constraints are from this icon up here, and the manufacturing constraints I have are single draw, split draw, extrusion, and overhang. And these just guarantee that your your optimized shape meets the requirements of whatever manufacturing process you might be using. And the icons pretty much kind of tell you the story of each one of the different manufacturing constraints. Single draw is used for casting or stamping, and if you're casting or stamping in one direction. So the icon, you can kind of tell here, the arrows indicate the plane that you're going to be working from with the draw or the casting, and it guarantees that you have nothing that no features that end up perpendicular to that, and any angles angle in, not out, so that your part can remove from the die. In the case of a split draw, imagine two single draws coming in both directions, which allows the angles to go out, but they must meet at the part plane and then go back in. Extrusion is used to guarantee you have a constant cross-section, so think I-beam. And no matter where you cut that I-beam, it's going to be the exact same cross-section. Extrusion guarantees that you have the same cross-section through your part. Interestingly enough, the most commonly used, in the case where extrusion is most commonly used, is in the case of, say, a laser or water jet cutting of a part. If you imagine you set a sheet of material down and you do a laser or a water jet cut on it, it guarantees you have a consistent cross-section through there. And we've got examples in the manual that show what each of those different manufacturing constraints would do. The final one we have is for an overhang. This is now specific to 3D printing or additive manufacturing, and it just guarantees the angle of overhang. So when I select that, I indicate the angle that I want, and that guarantees that I don't have an angle off of that plane that exceeds whatever is less than whatever my requirement is, and that just prevents us from having to use supports. In the case of this part right here, I'm not going to use any constraints or manufacturing constraints. I'm just going to rely on the symmetry plane here. And so that's pretty much it for the setup. In this next section, we'll talk about actually running the optimization and setting up the parameters of the optimization. With the model all set up, it's now time to prepare the optimization parameters, to set the optimization parameters. We're going to do that from the structure ribbon. We're going to come to optimize, hit the little play button. It's going to open up the run optimization window here. You can name your optimization. Just going to grab the name by the model name. But if you're going to be doing multiple optimization runs, I do find it rather convenient to give it a distinct name. So you can select it directly from the list there. We have a number of different types of optimization: topology, topography, gauge, topography, and gauge, lattice, and Poly Nurbs. Right now we're going to focus strictly on the topology. There will be some more videos perhaps in the future discussing some of these other ones. And when we talked about topology optimization, we talked about optimization. What we have to establish, in addition to preparing all of the geometry features, we need to establish an objective. An objective is what the optimization is looking to accomplish. And in this case, we have three main objectives, two main objectives and one sometimes used. But the two main objectives are maximize stiffness and minimize mass. That is effectively what the optimization is looking to accomplish. We also have maximize frequency, but for the most part, the frequency ends up being a constraint in either the stiffness or the mass calculation. So if we come to maximize stiffness, essentially what we're doing is defining that we want the optimization to distribute the material that remains in a manner that guarantees the part is as stiff as possible. But to do that, we also need to set some sort of constraint, because if you think about it, the part is as stiff as possible right now. Having all of the material there is as stiff as possible. So it would technically be done. And obviously the goal of optimization is to make the part lighter. So what we're going to do in this case, in the case of a maximized stiffness, is we're going to set a constraint, not a support type constraint, but an optimization constraint that will limit the amount of material that the optimization code has to work with. And that's what we see right down here with mass targets. And it says % of total design space volume. What this means is whatever number I select here or manually enter here, that is how much material from the design space, from the big red block there, how much material the optimization code has to work with. So it defaults to 30%. That is the default. After 30 plus years of doing optimizations, we've kind of determined that 30% is a good starting place, but it isn't necessarily where we're going to end, and we may revise that from there, but it's a good place to start. So essentially we're saying get rid of 70% of that big red block, and the remaining 30% has to be distributed in a manner that makes the part as stiff as possible. And here's where we come to where I mentioned frequency constraints. Most of the time, frequency ends up being an offshoot of another optimization. So now what I can do is I can maximize the frequencies to guarantee that the frequencies are as high as possible, or set a minimum frequency allowed for the lowest 10 modes. I know you're probably asking yourself why not just the lowest mode? And without getting too deep into the weeds, it has to do with a concept called mode swapping, where mode shapes can change their actual frequencies and move from the lowest to the second lowest or the third lowest or whatever. Look it up if you need a more detailed explanation. But it just guarantees that none of the 10 modes, even if they swap locations, ends up below 20 hertz or whatever you set from that. And then do we want to do that as unsupported or use the supports from one of our load cases? Thickness constraint, that guarantees the minimum value or the minimum thickness of any individual member in the optimized shape. If you remember that model that I was showing at the beginning of this video, you remember how it was kind of like truss type tubes? That guarantees how small any of those tubes can be. And then we also have an optional maximum that would guarantee how large any of them can be. The remaining values are the same as in the standard analysis, so we won't talk about those. And then you would just click Run. The other option is, of course, minimize mass. Now, minimize mass, the objective becomes to get rid of as much material as possible. And again, left entirely unconstrained, it would be a little sneaky, and it would do something like get rid of all of the design space and say, there you go, now it's as minimal as possible. So we have to set some sort of constraint on it. And in this case, the constraint becomes a stress constraint. And what happens is when we defined our material, or used one of the materials in the library, in there is a yield stress. The solver will take that yield stress, divide it by your safety factor, the default being 1.2. I think in this we're going to use 1.5. So take that yield stress, divide it by 1.5, and it will set that as a maximum stress value. As material begins to be removed, as it attempts to minimize the mass, the stress can go up. And if it notices that the stress is reaching or exceeding that 1.5 safety factor, then it will know that material has to be left there. So it's going to intelligently remove material based upon a stress constraint. And then, of course, the rest of these remain the same. We can define them as we want, and then we can click Run. Now, you'll notice that if we do minimize mass, we're not taking any stiffness into account. And if we're doing the maximize stiffness, we're not taking any stress into account. So a lot of times what people will do is they'll run both of them and then kind of take ideas from both of them. I can't stress enough that this is not a tool to design the part for you. We're not trying to take the engineer out of engineering. And anybody who says that their tool is going to design for you, don't listen to that. This is a tool just like your caliper, just like your calculator, and it's to help you understand information about your design at the beginning of the design process, to help you engineer a better part, not to do the job for you. So we're going to take information from this and we're going to engineer a part from this. So it's completely feasible to do a minimized mass, to do a maximized stiffness, and engineer a part with the information that we achieve from both of the analysis runs. And in addition to that, if we do minimize mass, one other option that we have to incorporate stiffness into the analysis, and we close that, is to come up to here, and if we come to apply displacement constraints. So in the analysis video, we talked about enforced displacements, but now we're going to talk about this, and this only applies to situations where we're doing a optimization, and essentially only applies to the minimized mass optimization because stiffness is already taken into account in the maximized stiffness. If I select this, it's going to say point, edge, face, or hole. And I can select it. So they say this this point right here. If I select that, it's going to put this kind of faded ball around there, sphere around there at 10 millimeters. So that's 10 millimeters from that current location. That seems a little excessive, so maybe I'll make it 5 millimeters. So what's happening now is when even 5 seems a little much, so I'll make it 2. There we go. What's happening now is, in addition to the stress constraint, it's also going to be keeping track of the overall displacement of that point right there, or what will ultimately be a node in the mesh. And it will follow that and make sure that it does not leave this sphere, this 2 millimeter sphere. The default is the sphere. We can also change that to a linear direction. So right now it's positive 2 millimeters from there. And I can also drag that or put it into negative 2 millimeters. So now this is just in the Z direction. And then I can put other different ones in other directions. Or I can just leave it as the default sphere, which is just a 2 millimeter in all directions. And that will allow us to incorporate a stiffness constraint to a certain extent in our minimized mass optimization, because it's going to be tracking to make sure that this doesn't move out of that realm there. And once we have everything set up, again, we just come here to run. The optimization will take a bit longer than the analysis. It is an iterative process, and it will go through and iterate, so don't expect results immediately. It does not typically take an excessive amount of time. And as with any of our analyses here, if it is going to exceed 15 minutes, half an hour, you usually will get a notification just letting you know to be aware of that. So this is not something you should expect results immediately, but they happen relatively quickly, and I think you're going to be pretty impressed with the results we get from that. So we're going to click run, and we'll see the results shortly. So our optimization is completed, and all I need to do is come up here to my little optimized shape, click that, and I can view my results. And you can see it's a pretty impressive result here. And taking a look at it, our original design volume was just under 3 kilograms, and now we're down to 1/4 of a kilogram. Actually, in its original design shape, I want to say it was somewhere around like 1.5 kilograms. This obviously, the design space is obviously substantially heavier than or more massive than the designed shape, but it's somewhere around 1.5 kilograms, and we're down to 1/4 of a kilogram. Now that we have this result, we can kind of take a look at it. In the Shape Explorer, we have this little slider bar. What this is going to do is it's going to just increase the material on all of our support members, and they were looking a little bit thin for my taste. And this is kind of you just kind of get the feel for what you want it to be. Its primary use is to eliminate things like this hanging load paths, or load paths that aren't well defined, so we can beef them up a little bit. So that looks a little bit better to me. And you can see that the mass adjusts accordingly with that change. So I can come through here and adjust that to what I want it to be. So I'm pretty impressed with the results here. First thing that a lot of people notice is it did abandon these 2 bolt holes. That was because we did run a minimized mass, a stress-based result. And essentially what that's telling us is those 2 bolt holes were not necessary to reduce stress on this part. Had I run a maximized stiffness, they absolutely would have grabbed onto there. The maximized stiffness is going to grab onto everything that it possibly can to stiffen up the part. But in the case of the stress result, it's not entirely 100% necessary to have those there. It felt that the material could be better used elsewhere. And again, this is why I say we're not designing the part for you. Maybe this is an aircraft part. Maybe the FAA requires that all aircraft door hinge brackets be attached in 6 locations. You're not going to turn to the FAA and say, well, no, the optimization says they're not necessary, which is true. They're not from a stress standpoint. But from a redundancy standpoint, we may want it there. So you're going to engineer in some result. And we don't have to rely upon the optimization code to give us that result. We would engineer this from us. In the next section, we'll talk about how to create geometry from this. But for right now, what I want to do is just kind of take an overview look at it. And then oftentimes, the very first thing I'm going to do is click the analysis button here, this analyze button. Especially if I'm doing a maximized stiffness. Since maximized stiffness does not take stress into account, you know for certain that it's as stiff as possible, but you have no clue whether it can support the load. We're a little bit more comfortable with the minimized mass because it is stress-based, so I'm pretty certain it's going to handle the load. But I'd still like to see the overall behavior of the part, so I just click the Analyze button. What this is going to do is it's going to take the part in its current configuration. So this exact part. So as a result of moving that slider back and forth, it is going to take this exact part exactly as it is, and it's going to take the loads and the constraints that I put on there, and it's going to run a quick analysis on it. And I'm going to be able to see the deformations. I'm going to be able to see the stresses. I'm going to be able to see everything on my optimized part. And you can see it did not take very long at all to run that. So I can just click my little flag here, and then I can click my animation, and I can view my animation. So there's my displacement of my vertical and my lateral loading. But what I'm primarily concerned about is the stress and the factor of safety. So if I look at the stress, you can see we're getting some more stress on this than we got. Let me stop the little wiggling there. Getting some more stress on this than we originally had. You'll see a lot of the stress is focused around these corners, but we knew that was going to happen. A corner is a stress riser, and we didn't want to take care of those in the design space. We want that nice big blocky design space. But I know that if I go ahead and put some fillets on here, which I will do, it's going to take care of that. And I can look at the vertical loading and the lateral loading. And now if I come here, I come back to vertical, and I come to factor of safety, you see my factor of safety is nowhere near where it was before, about 6 times factor of safety. What I can do now is come down here, and you'll see that as I approach that 1.5, which is where I did set my stress constraint, 1.5 times factor of safety, the entire contour disappears. So that tells me that this entire part has a minimum of 1.5 times factor of safety, and it will even improve again when I fillet these up. So I have met my design requirements. Check my lateral loading just to be certain. You can see again 1.5 times, everything's pretty much gone. And I have met my design requirements. So my optimization is a success. This looks like a good general configuration of the part to me. So what do we do now? I'm obviously not going to take this exact shape and send it to a 3D printer and say, okay, attach these to the airplane. We need to do something to get this now out of Inspire and into a CAD package, and that's what we'll discuss in the next segment here. So we've got that optimized shape. Where do we go from now? We need to get this somehow back into our CAD system to generate geometry so that we can create a part. And where you take it from now is kind of up to you. There's a number of people who will just take this overall design here, kind of take a look at it, and just go into CAD and design something from scratch based upon the information here. Another option that I have is to come here to this Fit Poly Nurbs in my Shape Explorer. If I select that, what's going to happen is Inspire is going to create some smooth poly nurb geometry that then can be sent back into my CAD system. So had I come up to, well, I got to wait a second for it to finish finalizing the geometry there. There we go. Let me turn that off. So now this is all geometry. Had I come up here previously and selected Save As, and then went to the type of model here, I can save this as geometry. But the only thing that would have saved would have been my non-design spaces, because those are my only geometry. Now this is all geometric. This is all solids. It's Poly Nurbs Fit. I would get this entire thing and it would go back into my CAD system. And I could create a nice CAD model from this. The other option would be to manually generate Poly Nurbs. That's a little bit more of a process, and in fact, I'll do a separate video entirely on that. But manually generating Poly Nurbs, I'm going to come back to my geometry here, and I'm going to use this tool here called Wrap. And what Wrap does is it detects the cross section of my part, and then I can drag down and create these nice tubes here. So let me just create there. We'll do that one right there, and then once I have those, I can come here and bridge these together. So I can select that face and select that face, and it will bridge them together. And I can create a real nice, clean geometry that way. And it's going to be a lot cleaner than the auto-generated Poly Nurbs, but it is a process that that does take a little bit of time and skill. And I'll create a video entirely on the Poly Nurbs generation. This part is really complex. It'd be a real complex part to do that on. You'd probably want to start on something a little easier, but we'll do a video on that. Just to give you an idea, though, of what somebody who's truly skilled at Poly Nurbs can accomplish, they took this and were able to come up with this shape right here. Let me turn off the original design space. So this geometry was generated entirely within Inspire, using the Poly Nurbs, smoothing things out, putting fillets on there, and you can see this is a design-ready geometry. I could generate a part directly from this. So you've got a couple of options depending upon where you want to go with it. You can do the automatic poly. You actually do nothing and just kind of take the idea and or the general shape of it, and use that as just a reference to design something in your CAD system. Maybe take some dimensions off of the part here in Inspire. You can auto-generate the NURBS, which will give you geometry that you could bring into your CAD package and use that as kind of framework to develop good, clean CAD. Or you could go as far as to generate the CAD entirely within, or the geometry entirely within Inspire here, using the Poly Nurbs, the blending, the bridging, and then the filleting to create a real nice geometric part that I could directly create a real part from. So that's it. That's kind of the basics of optimization. If you start using it, you can see some drastic results. It's not unheard of for 15, 20, 25% reduction in mass. And I've seen numbers as high as 50, 60, 70% reduction in mass, maintaining strength, or interestingly enough, in some cases, even improving the strength capacity, reducing the stress, making the part even stronger than it was before the part was optimized. So utilize Altair Inspire to make your parts lighter and as strong, if not stronger.